I'm now going to take over with my presentation, and I will be speaking on requirements-driven verification for safety compliance. I'm doing this in collaboration with an Artemis European-wide project called Crystal, where we've been developing this technique and a tool to support the technique, which is called the asureSIGN. So, regarding my agenda, I'm going to talk about safety in hardware and software. Holger gave us a good introduction to that. I'll expand on that a little bit, and I'll talk in detail more on requirements analysis and requirements-driven verification. And Holger mentioned ECC. I shall go into that example in a little bit more detail, how to break it down into a test plan, that I know we'll be speaking that on ECC regarding formal verification as well with OneSpin. So, as Holger mentioned, the markets for our hardware and our software and embedded products is expanding into lots of new areas regarding automotive, avionics, rail, nuclear, medical, which is the good news, but the bad news is most of those have safety requirements. As Holger pointed out, those markets often bring new development costs, which can make those markets unattractive. And I think Holger made the point very well that what we need to be able to do is not going to be necessarily the products themselves which determine our success in those markets, but also the efficiency of our development methods. Because as those safety requirements bring costs, we need to be able to ensure that we can develop our products cost effectively for those markets to make sure they're not too expensive. And again, Holger hinted at the fact that this will be and require us to use new tools and new methodologies, and those tools need to support the methodologies rather than hamper the way engineers can do their work. So what is safety? Again, Holger made a good point on this. He's saying it's not an exact science, and within this definition here, which is taken from one of the standards, you can see that there's an unacceptable risk there, and I think Holger mentioned unreasonable risk. We're saying this is unacceptable risk, which is not a particularly well-defined objective term, and also it hints at the fact that risk is not completely, you can't completely eliminate that risk. There's always a risk involved, and what we need to be able to do is to manage that risk in various ways in our devices. Risk, remember, is a product of impact and probability. So the way we normally reduce risk is to either manage the impact, and there's various ways of managing impact. For example, with fail-safe modes, we do a lot of work in avionics, where if the electrics start to fail, there's lots of fallback mechanisms within the plane which allow you to still fly safely. Ultimately, control goes back to the pilot. And we're going to focus here mainly on functional safety, which is the part of safety which makes sure that given inputs, we could produce the correct output from our system. So here's an example of a hazard which is involved in functional safety, a lane keeping assistant example. So lane keeping is there to increase the safety of our cars, or safety of the way we drive our cars. But such a function actually brings risk as well. So we must ensure that that new safety feature doesn't bring with it its own risk. So we can look at the severity of the impact. If that feature doesn't work, we can look at the probability, and as Holger mentioned as well, the amount of control which the driver has should something go wrong. And as Holger mentioned as well, what we do is we assign a safety integrity level to the functions. So here, this is an automotive example. ACLD is the highest risk that we have from a safety perspective in automotive, and you can see there that there is a reasonable possibility of life-threatening or fatal injury, and with little chance a driver can do something to prevent the injury. So once you've assigned that safety analysis, we'll see that means you have to do more from a safety perspective. So if you're at the highest level of ASIL, safety integrity level, that means you're going to have to do more to demonstrate that your system is safe. So we're talking about failure, and one way to start to think about that is how systems fail. Random failures, that seems strange that you can usually predict those, but random failures mean, for example, an error in memory caused by some sort of particle, alpha particle maybe, hitting memory and flipping the 1 to a 0. But we say they're predictable because statistically we can predict those. But also degradation in the silicon or the semiconductor are usually fairly predictable. We can take preventative activities, and we look at the ECC example, which is a good way of detecting errors in memory and correcting them if they're single bit and just highlighting them if they're double bit. What's more difficult, and which the standards really give us a lot of advice on, is the systematic failures, which is failures introduced by the way we develop our systems, and by definition they're very difficult to predict. If we knew where all the bugs were, we'd just go and fix them. And anyone involved in development realizes that it's knowing where the remaining bugs are is virtually impossible. The other failures are systemic failures, which is where basically the organization doesn't have the right culture, which we won't be thinking about here. It's more about culture and process. So the way the safety standards work, and again Holger hinted at this in terms of his saying about the proliferation of documents, is that the standards will define the processes, identify the processes which need to be followed, and then the objectives and outputs for each of those processes. And you're recommended to follow those processes and produce the outputs which they recommend. So for example here, this is IEC 61508, which is an industrial safety standard. This is talking about how we do a dynamic analysis in our testing, and you can see there HR means highly recommended, R means recommended, and as you get to SIL 4, your more and more becomes highly recommended. And you can see here a split between structural test coverage, which is code coverage, line coverage, branch coverage, MCDC at the highest level, modified condition decision coverage. But also there's some other cases there about how we generate our test cases. This is very from a software perspective, not from a hardware perspective. Boundary value analysis, error seeding, model-based test generation, performance modeling, equivalence classes, and input partition testing. Those techniques for our test generation. Okay. So as I said before, it identifies key processes. I won't go through these in detail. You'll have these slides afterwards. But one there is requirements traceability, which is one I'm going to focus on, requirements traceability. And as it said before, there's key deliverables. And Holger mentioned this, the proliferation of documents and deliverables, data that we need to generate, documents we need to generate, they all need to be reviewed. You have to store those reviews and proof that you've done those reviews. The information needs to be maintained. And then also assessed by an external assessor when they come in to assess that you've met the criteria for your particular safety integrity level. So there's a lot of data to produce, and this is where we need to find methodologies and tools which allow us to generate this data and store it efficiently. Some of this data needs to be stored for a very long time. I think in ISO 26262 it's 15 years that you need to store the demonstration that you followed the correct procedures. So I'm going to focus on traceability here. So traceability means that you define requirements, and that's not always easy. I think a few of us working in hardware and software development realize that requirements aren't always produced efficiently at the start of the development process. But in safety development, you have to produce requirements from the various stakeholders, which can be external customers and internal. You then go through a design process, which tells us we're going to implement those requirements. Then we're planning to verify those requirements, and eventually we do have the proof from our verification and our test results that those requirements have been properly implemented. So there's a traceability here going down, but there's also a traceability going up. You want to be able to trace back from your proof of implementation back to those requirements. Okay, so that's a very top level theoretical view. A lot of people do this via spreadsheets. I've got an example here. What we're finding though, as the requirements and the processes and development becomes more complex, these spreadsheets aren't really sufficient to hold those very complex relationships, and also to hold a history of the regressions and the data we're producing as we go. So as people move to more complex systems, the Excel approach starts to run out of steam. So what we're finding now is in order to support advanced verification processes is that there's a number of different verification metrics that people will produce. There's still directed tests, and Excel spreadsheets support well-directed tests, but they're not so good at supporting things like code coverage, functional coverage, which is a hardware verification technique, assertion passing and assertion coverage, which we use a lot in hardware verification. Quite often we want to see some software running as well, some software tests passing. It may be that we wait to the lab results and prove certain things within the lab, and or that we've actually used formal verification and the particular property has now been proved. Those relationships can be bidirectional or many-to-many, as that's shown above there, and they're very complex relationships. And those metrics can be from hardware, silicon validation, software testing. So what we're now seeing is a number of results, data being produced from within a wide variety of domains and disciplines. And what we want to be able to do is capture those results in regressions so that we can actually plot the progress over time, and also relate those back through this bidirectional mapping to how well a requirement is signed off. I find this very useful, that we can report to product owners, project managers, at a requirement level, progress at a requirement level, rather than always progress at a verification level. So we're very good at producing verification data. What we're not so good at is translating that into requirement sign-off, which we can do if you've got a bidirectional mapping like this. So I'm going to go into the ECC example here. I'm going to do this very quickly. You don't need to really understand these requirements in detail. But this is a typical hierarchical set of requirements for ECC. For example, the uncorrectable ECC error must always be reported to the local CPU, which is some interrupt can handle that, and there's various hardware verification and interconnect verification to do as well. Okay, so I'm now going to move into a demo of the tool. So this is our asureSIGN tool, and I've opened up the project here. The way asureSIGN works is that we're allowed to import requirements from other tools. So, for example, doors. I know a lot of people use doors, or other requirements generation tools. And the reason we use asureSIGN in this way and import is that tools like doors are very, very good at requirements management, not very good at requirements sign-off. And we can also import the software goals as well, software requirements. And we bring those into the tool here. Now we've imported those tools and we've got them under software here, so you can see, if I was to open the editor, you can now see that we've brought in the requirements from another tool, doors in this case, but we're not mapped to any tests yet. At the moment, this is just the requirements being imported. So I'm going to close this and now go to another demo, which is where we've mapped those tests to various verification activities, and now we've been running regressions on those verification activities. So here you can see the results of those regressions. If we drop down into some of the requirements here, you can now see that these requirements here, where before it was just a requirement, it's now been mapped to a particular test here, which is a directed test, which we would run in software to make sure that this particular requirement was properly tested. And there's a specification of the requirement. Here's the test itself. You might also have hardware verification techniques in here. So we've mapped to functional coverage points, and at the SOC level, we may have mapped to a number of cover bins here and cover points. So here what we're seeing is a mixture of test plan for both software, hardware, using cover points, directed test, constrained random, and also we'll see later that you can use this for formal verification as well. And here you can see that from the different levels of hierarchy, you can see the results of our regressions. We've run 4 regressions here, 1, 2, 3, and 4, and we can see from these milestones here that this actual results we got here from the regressions. We've hit our silver milestone. For example, here on the actual, we've got 50% coverage, which gives good enough for silver but not good enough for gold. And we find people, when they develop things, they've got interim milestones which they want to hit. And there's various other features of this tool which allow us to analyze those regressions. So for example, here we could compare the 2 most recent regressions and look at the differences between those regressions to try and find out what happened. Why did regression 4 do much better than regression 3, for example? Okay, I'm going to close that down and return to a presentation so we can hit our timescales. So as you've seen there, we're able to support hierarchical verification, and quite often a requirement must be signed off at multiple levels of hierarchy. For example, ECC will be doing a lot of hardware verification down at block level, and then some software tests to make sure it supports certain software features. As we move up to the SOC level, we then do interconnect testing, and at the SOC level, we may want to make sure that interrupts reach the CPU and get handled properly by software. When we go into the lab post-silicon, we may want to inject errors into the memory itself and make sure that and this is what Holger talked about, fault injection, to make sure those faults are properly handled within the silicon, and that they do get detected and corrected, or they get detected and passed to software. Okay. So here's a very brief overview of the asureSIGN data flow. We've pulled in requirements from different places here, into the tool. So we've now managed the requirements within the asureSIGN tool. We've taken regression results, and those results are fed in automatically. So if you're doing simulation, we read data from the simulation database. If you're doing proofs with OneSpin, we read the data from OneSpin automatically. If you're running software, we can read data from software test tools automatically. There's an API as well, so if you're doing your own scripts, so you can interface directly to asureSIGN, and eventually then you can do the proof of implementation for various reports, XML or PDF. I'm running out of time, so I won't go into too much detail, but requirements-driven verification has many different advantages. One of which, for example, is impact analysis. So if you want to change a requirement, you can see the impact on your verification. It's something that's quite often missed out when people look at impact. How much it will be how much does it cost to re-verify those requirements? And just in conclusion here, so as we're running out of time, these slides will be available afterwards if you want to read them in more detail. Certainly requirements engineering, requirements-driven verification, that proof of implementation is required for the standards, and there's more info about that, the Artemis project and asureSIGN online here. So at this point, I'm going to